Hello and welcome to this new video in our series on learning Agents.jl and Julia. In this video, we'll do something a little bit different, and you will see in a second. The screen that you're currently seeing is the interface of Pluto.jl, and Pluto.jl is a reactive environment for Julia. So you can very easily install Pluto.jl if you just add the Pluto package or the Pluto library in any repository and then call the pluto.run method after pre-compiling the Pluto package. And this will then open a web server which creates this interface where you can interactively run Julia code in your browser. And obviously this only works locally because you're running a Pluto server on your own machine. And to quickly demonstrate to you what that means, if you create a new notebook, this will set up a new file. Actually, it will only create a temporary file in the beginning. And this is a notebook. And these notebooks, I'll just zoom in a little bit, are very similar to Jupyter notebooks, with one very big exception. I can do things like assign variables, and then this variable can be used in another cell. I can do a +5, and this will then calculate a +5. So there are cells, and there's the output of cells, and you also get feedback about how long the calculation took. So if you're doing something in this cell, b equals 6, you can calculate that. And if you do a plus b, you get the result of a plus b. So this is basically running Julia immediately when you're executing the code. The big difference between Pluto and running Julia in VS Code is that Pluto is a reactive environment. And what does reactive mean? Reactive means if I change this up here to a equals 7 and press Shift and Enter, this will execute and update all other cells that refer back to the variable a. So this kind of behaves as if this is an interactive web interface. And actually, you can use it as an interactive web interface. You can add, if I press this plus button, I can add a library. For example, I can add Pluto UI, and this shows me, okay, it is available for download, and you don't have to use the package manager. It will automatically install this as soon as I execute this. And you see here the loading bar. This will install the Pluto UI in the background. Obviously this will take a while, but now it is installed. So I have now Pluto UI available. And one thing that I can do is I can assign a slider to one of these variables so I can interactively manipulate that. And I will do this in a second. I'll activate the interactive docs and the live documentation. And the live documentation will now, whenever I hover over something, it will show me the documentation for that function, in this case for the plus function, in this case for the equal function, and in this case for the Pluto user interface. And in the Pluto user interface, I now have a view of what are the interactive form elements that are available. And what I want now is some type of slider. Let's see, there is a slider. So let's try to add a slider, and we just say a equals slider. And what we see is, okay, this is how this should be used. We should not equal, a isn't equal to a slider, but we should have this macro called bind, then the variable, and then slider. And we can then give it a range from 1 to 10. And if I execute this, what will now happen is I have a slider which will refer to the number. And if I adjust this, all other cells that depend on the variable a, they will also immediately adjust. And I can add some additional values here. I can put in a default. I think I need a semicolon here then. Default equals 5. And I can also do show value equals true. And if I do that, then this is whenever you load this Pluto workbook, you set it to 5 and you get immediately feedback of what this number is. And yeah, that's basically the idea of Pluto.jl. You can save this notebook. You can even export it as a PDF file or as a Pluto file. And this is very helpful when you're trying out new things. The downside of this is it doesn't really work well with simulation in some cases, because obviously if you have an agent-based simulation, it has to run several iterations, and it is not like something that depends on a previous cell. And maybe one additional thing to know is that I cannot do something like C equals 7 and D equals 8. This is not possible. Multiple expressions in one cell is the error of this, which means there should only be one outcome of a cell. And if you want to do multiple things, you have to wrap it in a begin-end block, and the output of the cell is now whatever the result of the last line is. And that is one thing to keep in mind. If you're trying out something in Pluto.jl, you can use agents.jl in here, but whenever you're changing something somewhere, then everything else gets executed. And if your simulation takes maybe a minute, then every command that you enter will take a minute, and that is not what you really want. So I would suggest not using agent-based modeling in Pluto.jl. But I have shown you Pluto.jl because I do see something where we can actually use this. And this is, by the way, if you set up a notebook and you don't save it, it saves it as an interesting name. So in this case, surprising revelation.jl. And you can always go back to it even if you didn't save that. But what I can also do is you can have a URL that you can open, and this will also automatically scan the local directory. And there I have this file seir.jl, and this I will now open because this is a notebook that I have prepared ahead of time, because this is a so-called compartmental model which is an SEIR model. So susceptible, exposed, infected, and recovered is the idea of this model. So every person can go through one of these 4 stages. They're either susceptible, they have been exposed but are not yet infectious, then they're infected, then that's when they're also infectious, and then there is a state when they're recovered, and you can, in theory, by waning immunity, go back to SEIRs. So the idea here is that we are not solving this problem by looking at the individuals, but we're actually putting all the people in a compartment. So in the beginning, everyone is in the S compartment, and parts of this compartment, they move over to the next compartment, to the E and to the I and to the R. And we do not simulate probabilistically the change from every person to the next category. Instead of, we think about the problem and the dependent equations that are involved in trying to determine how many move from one field to the next. And in this file, we have all the function explained. And maybe another thing that is kind of helpful maybe is for every cell, you can press here on this I, and then the content of the cell is hidden and only the output is revealed. And there is a markdown output. If you're familiar with Markdown, you can basically type MD, 3 quotation marks and 3 quotation marks in the end, and anything that you will write in between will be interpreted as Markdown, and anything that's wrapped between 2 dollar signs will then be rendered using LaTeX or math, web LaTeX, so to say. This one said restart notebook because apparently it installed some libraries, and I will just click on restart notebook, and there we are back again. A package LaTeX strings not found in current path. Yeah, so it's installing it in the background, and I will close this as well. So this is on my local machine, and obviously I have to install all these libraries. It has already installed statistics, sparse arrays, linear algebra. And the one we're interested here in is ordinary differential equations. That's what we use. The LaTeX strings are these outputs here, and we have plots and parameters. And obviously we're going to use Pluto UI because we're running in a Pluto environment. So while this is working in the background, I'll explain to you how a differential equation-based model works and how we're trying to solve this using Julia. A differential equation-based model, the name already says it, is we have not a equation that determines how many people will be infected at a certain point in time, but we only understand the differential changes at any given time that are applied to the individual compartments. So we have the compartment S, which is the amount of susceptible people, and we define a differential, so the change at any given point in time, which determines how the amount of susceptible people will change over time. And this now looks quite complicated in the beginning, but it's not really. So the idea is here we have an R0 value, which is the amount of infections that you have per susceptible person. And the more people are susceptible, the more people can become infected. But also the more people are infectious, the more people can become infected. And this, so this determines how many people will move from the S department to the E department. So it depends on the number of susceptible, it depends on the number of infected, and it depends on R0, so on the basic reproduction number. And we have this additional parameter gamma in here, which will determine how much of R0 is translated into actual infections. And interestingly, you see there's a minus in here, and that's because we're not determining how many go into E, but everyone that goes into E has to leave the S compartment, and that's why we have a minus here. So these people we remove from the susceptible compartment. We're going to add all those from the recovered compartment who have waned their immunity. That's why the omega here is the rate of waning. And if you have waning immunity, then this determines how many move back from the R department to the S department, and that is added into the compartment of S. So that's what this first term is about. What you then see for the second differential equation is that if we determine the rate of change for the exposed compartment, all the people that we just removed from S, they need to be put into the exposed compartment. So all these are going in here. But not everyone it's not just the amount of people that are exposed is increasing, but also there is a rate of how the people that are exposed are actually becoming infected. And this is the second term here, which is deducted from E, because everyone who is exposed moves to infected at a certain point in time. So they have to be removed from this differential equation. That's why there's a minus sign here. And in the next step, we have the people that are removed here, they need to go somewhere, so we'll put them into the I compartment, and this is the differential equation for the I compartment, and all the people that go into I are the ones that have been exposed, and these are the ones, the gamma rate here is the rate of how fast people will move away into the recovered department. So this gamma parameter determines how fast people recover. And okay, we have a status update here. So this sometimes Pluto will give you updates on what's going on in the background. Let's see what it's doing. It is evaluating, so it's running in the background. That's nice. So we were here in this infected compartment. The last compartment is the recovered compartment, and people that go into the recovered department are the ones that leave the infected compartment. This is this here. And then we have the waning immunity, and this is this part of the equation. And this part we also see here. So overall we have 4 compartments, and anyone who leaves a compartment goes into another compartment, and we always have a parameter that determines the rate how they move between these. And in many cases, the rate of how fast people move from one compartment to another depends on the compartment size itself, but also on another compartment, depending if there's an infection process going on or whether it's just a timed process as for the later two. So how do we solve such a problem? One thing that we want to understand is when is the peak of the disease spread, depending on these parameters R0, gamma, omega, and I think we have sigma as well. So what we need to do to solve this is we need to define a function, And we call this function here simple SEIR because it's a very simple model. And the model consists of basically the differential equations. And let me format this so that you can see it much more easily. What happens here, these are the differential equations. We had ds over, so this is ds over dt, which is minus gamma r naught times s times I. And we have the compartments here as a vector. So we have a vector x, which is the compartments. And this one consists of 4 elements, the s, the e, the I, the r. So this x parameter here is this x parameter, and this is split in 4 different compartments. And what we need to determine, if we give it a set of compartments and we give it a rate, so the gamma rate that is determined up there is 1/18. R0 is here determined as R0, which is a parameter set somewhere else. I'll show you in a second. We have the sigma parameter, which is 1 over 3.2, and we have the waning immunity, which is here 0.01. So these parameters are used down here. So the gamma value is this gamma value, the R0, the R0 is used here. The sigma is used here, and the omega is used here and here. And if you're wondering, how did I write this R with a small 0, that's basically just writing LaTeX code, and you can use that as variable names. So you just type in R \_ underscore curly braces 0 curly braces. So how does this work? The idea is I put in an x, and what this function does, it computes the next step depending on the amount of time that has passed. And this can easily be achieved by just using the SEIRx. So we separate the x into SEIR, and we return a new vector, which is basically, this is a vector constructor. It says SEIR, and this looks weird. Let's put this over here, and let's put this over here. So what this does is here in this case, it removes what we've seen up there, and it adds the waning immunity. This is, by the way, not mentioned in the comment here because I think I added that later. Omega R is added here, and here is where that is removed. Everything else is still correct. Gamma I, yeah. So this calculates the new S, this calculates the new E, this calculates the new I, and this calculates the new R. Obviously, this is kind of wrong because it doesn't use P, it doesn't use T. We don't really know where this is going, but that's not really what we need, because we only need a function that determines this from the input and the additional parameters that are given here. And the idea here is that an ordinary differential equation is defined as a function that depends on t, and that's also something because we assume that these changes here are true for infinitesimally small t values. So the smaller t, the more correct this equation is. And what we now want to do is we want to figure out what happens with this function over time. Can we approximate the real outcome from this differential description? And that's actually not very easy. At first you might think, okay, if we know the gradient of the function, can we not just trace the line? Yes, if we could trace the line in infinitesimally small steps, but that is not possible. So the easiest method is the Euler method, where you just go in steps of 1, but that will obviously under or overestimate the function depending on the gradient, because it might. So if you're going in steps of 1, the differential might change in between. And if, for example, if you have an exponential function, then you're underestimating the increase. So how do we solve this? The idea is that for any differential equation, we determine a start condition. And the starting condition we here define as a x0, and the x0 is a s0, e0, i0, and r0. And in our case, we basically just say I0 is 1 to the power of 1 times 10 to the power of -7. So we put this in fractions. So depending on the size of the population, if we have, for example, 3,300 million in our population, then 1 times 10 to the power of -7 means we have 33 infected people in the beginning, and we do not have any exposed. We could have some if we wanted, but we don't need any. We have S0, so in the beginning, everyone, so 100% of the people of the population is susceptible, and no one is recovered. And this part of the formula is only in here if you want to start with some people that are exposed, but in this case, I just removed that so you can ignore what is here. The question now is, what do we want to simulate? We have to determine how long our simulation or our calculation should work. And we define this as a tuple, which is a time span. We can give it any variable name. We give it this one. It goes from 0.0 to DUR, and DUR is defined below that. And that works only because we're in Pluto and the variable can be anywhere on the file. And then we have a problem definition. The ODE problem consists of the ODE function, the starting condition, and the time span over which we should find the values of the function. And then we have a so-called solver, and we create a solution using the solver and the problem, the one that we've defined over here, and we give it a function. If I mentioned to you the Euler method, I could have the Euler method in here, but one that works kind of well for these types of problems is the Cituras 5 solver, which is, if you're familiar, a 4th order range cutter interpolator. And in this case, it works well because we have a so-called non-stiff ordinary differential equation. If you don't know what that means, that's okay. In this case, if you want to read up on that, you can have a look at all the different differential equation solvers that are available. And we are just using the ordinary differential equations. There's also the differential equations package, which has even more different functions because it kind of depends on the complexity of the formulas that you've used in your differential equations, which type of differential equation you have, and what type of solver you need. So what this now does is it provides a solution, which is, if I click here on more, the amount of, I'm sorry for already previewing the result. So it gives you for every time step a value for SEIR, and this is the starting condition. And the TSIT solver, it automatically determines what are ideal timestamps. So this is not 0, 1, 2, 3, 4, and so on, but it tries to define points where we have interesting changes in the curve so that from that we could then print a solution. So the TSIT5 does not provide a systematic change in the x direction. So what does this do now? We have now here a slider, and this slider is bound to the R0 variable. So if I show you the code, it basically says, and this is now a little bit harder to read, here is the R0 slider, which means the variable R0 is bound to this user interface, and it goes from 1 to 42 in steps of 0.1. The default is 3.5, and we will show the value. I'll hide this again. So I can change this here to produce a new outcome. And the other thing was the duration, and the duration is the duration of the simulation, and it was, I think, 365 days. Let's have this longer year. And this is what the outcome of the solution is. If I plot the solution and I give it labels, so that, by the way, the L in front of this string just means it's a LaTeX string, and if I put an S in there, you see it's italicized. That's the only thing why there's an L. There's the title, and the line width is 2, and the X label is a italicized T, so for time. We could also have Y, but that's the Y label doesn't really make any sense because that's maybe percentages we could have under here. So what does this now do? By changing the R0 value, for example, to 8.9, this is a much more infectious disease. It has more people infected for every person. It has more people exposed for every person that is infected. we now see that we have a much sharper increase in the amount of infected cases. And I think we have a slight recovery, or the recovery, a slight waning of immunity, because it was set to 001. We can set this to 000, so we don't have recovery. And then you will see that at a certain point in time, everyone will be recovered and no one will become infected again. So the infections go up and they go down, and this is where the height of the curve is. And if we make a less infectious disease, we will see quite a different result, where the height takes much longer to reach, and it is also much lower. And that is basically what is what was some of the main ideas during the first wave in the pandemic, is trying to lower the R values so we can have not as many people ill at the same time. So let's add in, where is it? Waning immunity. Obviously, these parameters, this omega here, could also be bound to a slider. You could add your own slider, and I will share the code with you so you can experiment with that, with a different slider here, where you would define a variable omega, and this omega is then added here into this parameter in the model, and then you can adapt the model to your own questions. You could also do that for gamma and for sigma. So that is relatively easy to do, but I didn't do it here, so you have something to try out. An important thing to keep in mind with differential equation models is that these models, they work on the assumption that there is an infinitesimally small subpopulation in every population. What does that mean? So even if we have now 330 million people, if we would assume this was the American public, for example, the value for each of these functions can vary in an amount that is smaller than a single person. So in theory, in a compartmental model, half a person can be infected, or 0.1 person could be infected. And the result of that is that if you have waning immunity, you will always have the disease remain, and it could, let's see if we extend it, you will here see that there is some wave going on, and then this curve stabilizes. You will never see a disease die out in a compartmental model because you will never have exactly 0 cases. And that is the only case when there is no infection happening, when the differential will just stay at 0. And we can quickly test this. If I do 0 here and comment out the E-7, then you see if there is no person infected, then we get this. But if we put in the tiniest amount of infections, like to the power of -17, we still get a full wave infection. Even if this number doesn't make any sense, this is a 0 with 17 zeros after the decimal separator. Before there is a 1, and I think we don't have enough people on this planet to have this little amount of people infected. So just as a heads up, this is the consequence of compartmental modeling, and especially of differential equation-based models, that you will never see a disease die out unless you exactly hit 0 in one of these iterations, which will never happen. So I hope this gave you a brief understanding of how you can try out the Pluto package, and in particular our SEIR simulation. In the next video, we'll try to add a compartmental model or a differential equation-based model into our agent-based model, because these models can be combined with one another. We can have a compartmental model to simulate the influx of infections from the outside by simulating the rest of the world, where we don't need all the complexity of the individual behavior. We just assume there is some infections on the outside, and the higher the amount of people infected, the more likely it is that we have an influx of infections. And that is something where we can combine the differential equation-based model and the agent-based model to inform each other, and this is what we will do in the next round. We will not do this in Pluto JL, however, so it will not be as interactive as here. It will be the slow process of coding and developing it, and then seeing the results in the interactive version maybe, but you will not have this immediate effect as in Pluto.jl. I hope you found this interesting. I will post a link to a GitHub repository where you can download this workspace and then can play around with it if you would like to. Maybe one thing I can quickly show you is how you actually activate Pluto.jl. And here we have some errors in the background. That's not too bad. I cancel this by going Control C, and now Pluto has been closed. So if you're in this repository, oh yeah, there was a problem here. So this doesn't matter. I'll upload this file and you will have this file. And if you're in the repository where this file is, or if you're in this directory, you can basically do using Pluto and then do pluto.run, and this will activate your Pluto environment, and that's it. So it's as easy as that. If you get an error message, that would mean that you don't have Pluto installed, so you would have to go into the package manager mode by going closing bracket, add Pluto, which I don't need to do because it's already added, so this will have no changes. And then you can do using Pluto and pluto.run. And this will allow you to execute the SERR model on your machine. You just have to put the file in one directory and extract the zip file. And yeah, that should get you going. It will take a while to install all the libraries, but it shouldn't be a problem. I'm looking forward to seeing the next one where we'll integrate agent-based models and compartmental models.